Hey all, how you doing? This is a video about phylogenetic trees and relationships, kind of fundamentally, and then more specifically using genetic codes and different ways we do it. This is just an image I grabbed from Khan Academy, and this is a phylogenetic tree. And basically what this does is it really just shows relationships, and there's a lot of different ways that you can show relationships, and so that's what makes phylogenetics interesting, because you really are in essence deciding to some degree what it is you're comparing. So in this just generic idea, just to show you the layout of how this one works, there's basically an ancestor, and if there is an ancestor, it's typically called a root. It's a rooted tree. And then A, B, C, D, and E have to basically are 5 different organisms, and this chart shows their relative relationship to each other. So you can interpret that A is the least related in whatever the categories of relationship to E, and that D and E are the most related, and then B and C are more closely related than B and D. And so that kind of is one beginning way to understand how this works. The closer things are on a branch, and these are branches, the more related they are. So this one just happened to be separating some kinds of different mice or whatever by whether they had fuzzy tails or not, or big ears. So clearly we can interpret, like, did A have a fuzzy tail? The answer is no. And then after this point, all the rest of them had a fuzzy tail. B had a fuzzy tail, but B did not have big ears. C and D and E had big ears. And then in terms of whiskers, D and E both have whiskers, and so that's why they're both on this particular branches here from this node right here. So that's a fundamental understanding of it. And let me just show you one other example. You can see here, this kind of shows in essence the relative same idea as the previous one. And so I'm going to ask you a couple questions about that right now. As you probably noticed, I'm not one to put a lot of words on a lot of my videos, because I like to teach by example, but this is one exception to that, and I kind of want to give you a sense of what signs and lines are. Let me get that out of here. And basically, these things are short and long interspaced nuclear elements, and they are repeated non-coding sequences that are large parts of eukaryotic genome, and we have a lot of short ones as humans. And so the reason that we look at things like signs and lines, and by the way, signs are the ones we tend to use more to look for areas that we might be able to phylogenetically compare organisms, especially in an evolutionary sense. The reason they're great is because of some of the problems we have with some other issues with how we do this selection. You can see here that the problems we have a lot of times in phylogenetics is, so much variation of similarity. In other words, there's so many different ways to compare how similar things are in different ways. How do you choose the right one? And then, of course, the idea of how those might relate to some sort of evolutionary relationship. So these two have been indicated. Signs are used a lot more in general for some degree of phylogenetic comparison. And generally speaking, it's because they tend to not code for protein coding parts, which is good. And there's other reasons as well. And so these are some of the features, I don't know why there's a line there, of why we can use them. Number one, the signs are either there or they're not, which is great. So it's a kind of a great place to add a new branch from a node. They seem to be inserted randomly, which is good. And so because of that, the randomness, it means that there's not necessarily an evolutionary pressure to it, and that's really good, because then if one organism doesn't have a sign and then the 2 or 3 other ones do have a particular sign, then you can assume that those 2 or the 3 are related and came after the one that didn't. And so if that kind of makes sense, so that's where they come in, and they appear to be irreversible, so they don't disappear, which is great. So once they're there, they're kind of there. I mean, except for some larger translocations, which would be indicated by a lot of other things missing as well. And so they also imply the order of who branched off first, depending on when they showed up. So that's why they're used. And so knowing kind of like the fundamentals of a phylogenetic tree, I'm going to kind of do some simple relationships with some DNA to kind of show you how we would build some of these trees using sequences. But before I want to do that, I want to go over this picture in your book. And basically what this is this is a tree based on signs. And this was one of the ways we looked at the relative evolutionary relationship between some organisms. And so to help you kind of identify this is a root right here. This is called a rooted tree because there's some ancestor, and you can see that the camel doesn't have any of these signs. And at some point, this I know ARE sign, that's what the arrow means, is that that's where that showed up. The camels don't have it, but everybody else does. And then if we do further separation, we see that out of the ones that had the I know ARE, there are two groups that had another I know ARE right here. And then also a GPI ARE and a Pro ARE. And these are basically just all the insertion points of all these different signs. And so you can see here that the organisms on this, the pigs and the, I believe pronounced peccaries, but it could be pecaries. I think it's peccaries. None of them have any of these four signs, but all of these organisms do have these four signs, and as we go down the line we can kind of see that. And so therefore we can use these signs as one way to show relative relationships. And the funny thing here is what this showed, as you can tell, is that the hippopotamus seems to be way more closely related to whales than other land-dwelling organisms based on this particular use of signs. So let's take a look at a simplistic example like this. So consider 4 different species that have homologous sequences of the 4 of these: ATCC, ATGC, TTCG, and TCGG. And then basically we're going to use the number of differences as a way to measure how dissimilar they are in order for us to be able to produce a phylogenetic tree from this. So obviously let's just kind of go ahead here and make this. So obviously the distance between these is 0, as you can see down the line, because those are clearly the same sequence. So what's the difference between A and a T and a C and a C and a A and a T and a G and a C? And you can see that there's one difference. And so because of that, we put a number 1 right there. And so that is what we're going to do to create the entire rest of the tree. I'll do one more for you. So what's the difference between ATCC and TTCG? The obvious answer is that this is different, right? We have a T at the beginning and here's an A. Then we have a T and a C. There's a T and a C. And then the G is different. That should be a C in the other one. So because of that, we have a difference of 2. So let me go ahead and fill out the rest of the chart real quick. All right, so here's what the completed chart looks like. And then basically from this point, we need to find the smallest distance, which by the way would be the closest relationship. And as you can see here, we clearly have that. The relationship between this, whoa, that's not what I meant to do. Well, let me go ahead and, okay, let's do a little undo. Sorry about that, guys. So the relationship between this and this, right, is 1. And so they are going to be the closest. And so I'm going to real quick copy paste a picture of what that particular branch would look like. So as you can see, these two are so far the closest related, the ATCC and then the ATGC. And so now what we do is we have to basically reduce the matrix. And so what I mean by reduce the matrix is I'm going to basically kind of rewrite this and then see if you can figure it out and then explain it to you. So now you'll see what I did, where I basically just combined the two more simplistic ones and just to add them back so you know what I'm looking at. So there you go, I just added that back up in the corner. So what you see now is I combined these. And now when I do that, I got to figure out its relationship between both of these. So I'm going to do it, I'm going to take the average of it. So to explain what I'm comparing, the first time I'm going to compare this, just TTCG to AACC, and I can see that there are 2 differences there. The T and the C in the middle are the same, but the A and the C on the end is not. And then I'm also going to do the same thing with this and not this anymore. But now I'm going to compare it with this. And now that I have that, I see that there is a difference of 3. It looks like the only one that's the same is the t, the second t right here. So so basically what I have to do from that is I then have to take the average of those. And so I'll just kind of just do it like this. And then go ahead and do a divided by 2 sign. We'll just do that. And when we do that, we get 2.5. And so that is the average distance between that. So now I can erase all this because now that you've seen that. And I'll just repeat that process for all the other ones. And so let's take a look at this one. So let me go ahead and remove this for you, just visually. And again, my suggestion is that you stop the video and try this one out yourself and let me know what you get. Alright, so it looks to be there's a TC, GG. There is nothing the same, so that means, in other words, the difference between this and this right here appears to be 4 things, all 4 of them, so that's going to be a 4. And then the and then the second one, whoa, let's try that again. Second one looks like there's a difference of 3 because the G is the same. So that's going to be 4 plus 3. And then I'm going to take the average of that, or basically times half, and I'm going to get 3.5. And I repeat the same process down here. This is the same, super easy. There's 2 differences between it. Great. So now I've reduced the tree to look like this. And so now I'm going to say, okay, well, in that case, what is the closest relationship that I have? And I have TTCG and TCGG. So that's going to be another branch like this. So let me show you how I would write that. So that is how I would write those. And so now we kind of have to put all this together. And again, we can once again condense as well by linking all the clusters together. And we get the following as a product. So this is what we get for the tree, and you can see here now that we've added numbers. Some places use numbers, others don't. I always find it's a good move. And the idea that makes sense, if you recall, the distance between ATCC and ATGC from the very top was a 1. And so that's why it's going to be split between both of them. And then the distance between the TTCG, that was 2. And so that's why it's split between 1. And then when we include the rest of the information from all of the generic trees, we get basically a split of 3 divided by 2, and then this is kind of what it looks like. So this is just example 1 of taking a matrix like this. I'm going to show you a little bit more on the nuance of how we can combine these, but that's the kind of first intro video to show you how we might use this.